Hi, welcome to environmental chemistry video number 3, where we'll talk about ozone depletion and oxygen dissolved in water. Um, First of all, when we're talking about ozone, the most important thing that we need to know is why is it important to life, and what is it, how did it form, all these kind of things. So the first thing that we need to know is then that ozone is a natural layer of O3, all right, ozone, that gets formed in the atmosphere around somewhere between 12 to 50 kilometers above the sea level, all right, and it is produced by the breaking of the oxygen-oxygen double bond to create single oxygen atoms or oxygen radicals, which can then react with another oxygen molecule to form an ozone molecule. Now, one of the things that ozone does is, because of its particular bond order, notice that ozone has a resonance. You can have either a double bond or a single bond, but the reality is that that's not the proper way to think about it. Ozone has an oxygen-oxygen 1.5 bond, basically, because the double bond is spread out between the two atoms. Because of that difference in the bond order, the bond strength, the enthalpy to break that bond is going to be different. All right, so let's look at some numbers over here for a moment. If we look at the formation of ozone naturally, all right, the oxygen-oxygen double bond requires ultraviolet radiation in the norm of 242 nanometers. So it actually is high energy. All right, the wavelength is going to be smaller. That's going to break it into two oxygen atoms. All right, and again, like as I said, when that oxygen radical reacts with an oxygen molecule, it creates ozone. Bond breaking is endothermic, bond forming is exothermic. So overall, we need to absorb that ultraviolet radiation in order to make ozone. All right, naturally in the atmosphere, as ozone gets hit by ultraviolet radiation, the wavelength that causes the breaking of ozone is around 330 nanometers. All right, so it's going to be a little bit lower in energy. The longer the wavelengths, the less energy that a photon carries. All right, so when ozone gets hit by this 330 nanometer ultraviolet light, it breaks into forming an oxygen radical and an oxygen molecule. That process too is endothermic because it's bond breaking. The oxygen radical can bond with another ozone molecule to give you two oxygen molecules in an exothermic process, and that starts the cycle again. Those oxygen molecules can be rebroken by a high energy photon, the 242, and make some more ozone that way. This process is constantly happening in the atmosphere, and the concentration that we saw that we had for ozone is what's called the steady state, because it does not generally change. We have a constant rate of formation and a constant rate of depletion. You know that when we have constant rates, both of the formation and the consumption of a substance, we have an equilibrium. So we have something very close to that, which we call the steady state. Unfortunately, air pollutants have actually disturbed that rate and actually can act as catalysts in the decomposition of ozone. All right, and those air pollutants then cause more ozone to be broken than it's being formed, and therefore that causes ozone depletion, which eventually results in an ozone hole, an area that is so thin in ozone that most of the ultraviolet light passes through, which can then have negative effects on living organisms, because it can cause increases in mutations and therefore in cancer. All right, so two of the main things that cause or that catalyze the depletion of ozone are nitrogen oxides and CFCs, chlorofluorocarbons. All right, and so here I will show you very quickly one of the processes. Nitrogen monoxide is already a radical. All right, and when it reacts with ozone, it will create the nitrogen dioxide radical and an oxygen molecule. The nitrogen dioxide radical will react with atomic oxygen that is just floating in the atmosphere, all right, to give another nitrogen monoxide and another molecule of oxygen. So basically what's happening is that the NO2 is trapping the atomic or the radical oxygen that would react with an oxygen molecule to form ozone. So not only are you breaking ozone in step 1, you're also trapping the starting material for making more ozone, for replenishing the ozone. This, as you see, becomes a cycle. This is why it's catalytic, because the nitrogen monoxide can continue to do this in a what we normally would call in a mechanism, in a propagation step, and we just keep on going over and over again. Here in this little side image, you can just see basically what's taking place. I can see that there's a radical sign missing, so I'm going to put it in there. Because it's atomic oxygen that we're talking about, so we're going to have some of that continuing. All right, so excuse me. The other thing that I want to show you is that CFCs, chlorofluorocarbons, all right, which were used as propellants in canned air spray and all those kind of things, hairspray, actually react with the UV. The UV will break the carbon-chlorine bond, all right, creating two different radicals. We'll create a freon radical, which we don't really care about, but we are also creating the chlorine atom or chlorine radical. The chlorine radical will react directly with the ozone to create oxygen molecule and this chlorine monoxide radical. The chlorine monoxide radical can react with also, again, trap some of that atomic oxygen to create oxygen molecule and recreate the chlorine radical that will continue depleting. Now, if we really want to know more carefully about this, I can show you this image over here. We have a chlorine carbon bond that breaks homolytically. That is basically what we have here. We have a homolytic cleavage of the bond. One electron goes in one direction, one electron goes in the other direction. So one electron goes onto the carbon, the other electron goes onto the chlorine, creating the chlorine radical. The chlorine radical can, as we saw in the previous version, react with ozone, all right? And after it's reacted with the ozone, it's going to create the chlorine monoxide radical and an oxygen molecule. Chlorine monoxide radicals can react together, all right? Like we see in the second step. This is more information that the IB requires, so I'm just showing it very quickly. The chlorine monoxide becomes this dichlorine dioxygen, which breaks to create this chlorine dioxide plus a chlorine radical. The chlorine dioxide breaks down to form oxygen and another chlorine radical, both of which feed into the decomposition cycle. All right. Now, obviously, this is more complex. We are just going to worry about, this is a simplified version of that process, okay? Because all we're looking at what happens with one chlorine rather than introducing a second one into the place. All right. Now, CFCs again comes from refrigerants, aerosols, all these kind of different things that we use. Hopefully, we will eventually stop using them. We are in the process of eliminating them. Certainly, they're no longer used as propellants in aerosols. All right. NO is a little bit more complicated because nitrogen monoxide gets formed, remember, from the high temperatures in the internal combustion engine. Plane engines are putting nitrogen monoxide directly into the high atmosphere where they can affect the ozone. All right. And remember, chlorine, the CFCs, the chlorine atom that they form, and the NO act catalytically. So this is going to have a very long impact. As we talked about the impact, of course, we have more UV radiation reaching the surface, so it's going to create more damage to DNA, mutations, cancer. It also causes problems with phytoplankton and therefore the food web in the seas, which is covered most 2/3 of the surface of the planet, are going to be affected. Now, we can't do much about NO right now, but we can do things about CFCs, and in order to do this, we are going to look for substances that have similar properties to CFCs, that they are gases, all right, first of all, obviously, that they have low reactivity, they have low toxicity, low flammability, but have no carbon-chlorine bonds that can be broken by the ultraviolet light. All right. So some of the alternatives, hydrocarbons, are good. They're low reactivity and low toxicity, but unfortunately they're flammable, so that's not great. And some, of course, they all have a small amount of greenhouse effect. Fluorocarbons, instead of having any chlorine, they're completely fluorinated, so all of them are carbon fluorine bonds. All right. These are quite good, but they're very expensive. But the carbon fluorine bond is not broken easily by ultraviolet light, so that's a good option. Hydrochlorofluorocarbons have one chlorine carbon bond rather than two chlorine carbon bonds, and so that's going to be not too bad. They tend to be broken down lower in the atmosphere, so they don't get to affect the ozone layer as much, but still have a carbon chlorine bond, so that's not ideal. Hydrofluorocarbons are the best alternative that we have because they don't tend to have, they're not toxic, they're low reactivity, and they're a little bit cheaper to make than the perfluorinated, the completely fluorinated hydrocarbons. All right. The problem with any of these, including CFCs, is that they are all contribute to the greenhouse effect, and that is a big problem that we have. Now we're going to go ahead and move into the dissolved oxygen in water. Okay, so here we go. When we're looking at dissolved oxygen in water, it's a measure of how pure the water is. All right. Normal water will have a certain amount of oxygen dissolved because of the atmospheric pressure of oxygen on it. Because oxygen is 21% of the atmosphere at regular temperature around 20 degrees Celsius, which is the normal temperature for water in a normal day. It's about 9 ppm, 9 parts per million of oxygen that is dissolved in the water. Most fish require a certain amount of oxygen, somewhere between 3 ppm to 6 ppm, to actually survive in water. All right. Obviously, bacteria, being able to be aerobic or anaerobic, will not require too much oxygen to survive. All right. Now, the amount of pollution, and in particular organic pollution, in a water body, in a body of water, is called the biological oxygen demand, or BOD. All right, and BOD is the amount of oxygen required, all right, for bacteria to break down all the organic waste matter that is present in a water sample. All right, anywhere less than 1 ppm of oxygen would mean that the water is nice and clean. Anything that is beyond greater than 5 ppm is considered to be polluted. All right. So again, this is not the oxygen that is necessarily dissolved in it. This is the oxygen that you would have to have dissolved in water in order to get rid of all the waste. All right. The BOD is measured by the Winkler method. All right. The Winkler method is just a way of measuring, of oxidizing the organic waste, and measure how much oxygen would have been necessary for this. All right. So how is the Winkler method done? Here's a little quick description of how it's done. All right, you're going to first of all saturate the water with oxygen by actually bubbling at high pressure oxygen into the water sample. All right, you're going to allow the sample to incubate there for about 5 days in order for the bacteria to consume the organic waste. Then we're going to use alkaline magnesium 2 ion, all right, which will be oxidized by any leftover oxygen. All right, adding acidified iodine ion, all right, we'll get a certain amount of iodine, which can finally be titrated. Yes, it's multiple steps by thiosulfate. At the end of this process, you can, and using balanced equation for this, you can actually find out how many moles of oxygen were present still at the end in the sample, and so you can make by difference how much was the biological oxygen demand, how much oxygen was taken up by the bacteria in order to get rid of the waste. All right, this whole process, I'm only outlining it very quickly. You can see this in your textbooks with the actual reactions, but the most important thing is that in the presence of oxygen, we are going to get the aerobic decomposition, which is the more natural process. If there's enough waste and too little oxygen in the water, we're going to get the anaerobic decomposition, and that's what's going to give us the foul smells of stagnant water that is rotting. All right, so here are some of those products. I actually put this table at the bottom, so let me just show you what they are. All right, so if you have carbon, the aerobic decomposition products are CO2, carbon dioxide, which doesn't have a smell. The anaerobic decay is methane, also does not have a smell, but it is kind of like one of these hydrocarbons. All right, hydrogen aerobic decomposition is going to be, or decay is going to be water, while the anaerobic is going to be involved in making methane, ammonia, hydrogen sulfide, and also some water. Oxygen, regardless of whether it's aerobic and anaerobic conditions, obviously if you have oxygen, you have somewhat of aerobic conditions, you're going to make water. Nitrogen decays. Any nitrogen in a sample in the waste products are going to decay to make nitrates in an aerobic condition in presence of oxygen. But in absence of oxygen or not enough oxygen, you're going to get ammonia and amines. And amines are those that they have a smell of rotten fish. It's quite a strong odor. Sulfur, the sulfur present in the waste, in an aerobic will go to sulfate. In an anaerobic conditions will go to hydrogen sulfide. Hydrogen sulfide is that very characteristic smell that rotten eggs have. All right, and finally, phosphorus decays in aerobic conditions to phosphate, and in anaerobic conditions into phosphine, which is also another foul-smelling and toxic material. So the aerobic decay products tend to be much more benign, less toxic, while the anaerobic products tend to be toxic. All right, so this is one of the reasons why we worry about waste, because if there's a requirement for too much oxygen, we're going to decay, or we're going to decompose into the anaerobic products. All right, coming back over here, so if we have competition for the oxygen present in dissolved in water, all right, the bacteria are going to tend to use it up before fish or other larger aquatic life forms can use it, and therefore that's actually going to be negative. Now, any water that is moving has a natural mechanical way of getting some oxygen back into solution, because you can get rid of some of the other byproducts and get some oxygen to redissolve from the atmospheric oxygen. All right, anything that has low flow problems, all right, characteristics like lakes and ponds will tend to have more problems with aqueous pollution and waste, organic waste in the water. All right. Now, the process of eutrophication is an important one. It's a process in which you have excess nutrients, such as nitrates and phosphates from fertilizers, all right, that will cause algae blooms. Algae blooms, when there's too many algae growing, they are going to choke out the life because they are going to be consuming all of the dissolved oxygens, all right, all of the dissolved oxygen in the body of water. All right, that will cause more decay, as then eventually the algae too will die, which will of course create more nutrients for other bacteria, and the cycle continues. So you continue to get more foul as because of eutrophication. All right. So the final thing is temperature. The amount of a gas that can dissolve in a sample of water is inversely proportional to temperature. So it's because of the motion of the molecules. The lower the temperature, the more you can dissolve a gas, because it is less likely that it will come out of solution because of motion. So, and it also allows for the very weak intermolecular forces that cause the dissolution to take place to keep the oxygen in the solution. All right. So if we have thermal pollution, for example, water that is coming out of a power plant that is used for either hydroelectric power plants or for coal or oil burning power plants. All right. Those will have less oxygen, and therefore the rivers that are coming into which the warm water is being put into will have less life. All right. So this can also affect the rates of fertilization and egg hatching. So how do we deal with this? Well, thermal pollution can be normally done by actually allowing the water to flow through porous materials. All right. Also bubbling more oxygen into it, so the heat is transferred into the air, all right, into the porous material, and the temperature goes down and more of the oxygen can be dissolved. All right. Thank you so much. Watch video 4 to continue with environmental chemistry.